Hey, Nick Kushner here again. Today I'm going to be this is like part 3 of my video on guitar physics. Today we're going to talk about tuning systems. So one thing that always drove me crazy about the guitar was this constant obsession to keep it tuned all the time. After I would get it intonated by a guitar tech, I would put it through the tuner, and certain chords or fragments would still sound out of tune to me. I tried to understand what is going on. I later learned that there are different tuning systems. The two popular ones are called just intonation, and the other is equal temperament. The piano and guitar are tuned according to equal temperament. So what are the two? What are they two about? So first I'll define the just intonation. Here, just intonation is a system of tuning limited to one key and aims at making the intervals as accordant as possible with both one another and with the harmonics of the keynote and of the closely related tones. Most of the frequency ratios can be expressed in terms of comparatively small numbers, indicating consonant harmonies. Violinists and singers prefer just intonation. The major disadvantage for a justly tuned piano is that switching keys results in major tuning problems. So let's just go into this a little bit in depth. So Pythagoras just demonstrated that when you play a C note and the G note above, the perfect fifth above, the ratio of the G note to the C note frequency is 3/2, or 1.5. And I'll just show that right here. So here's your C note. C has a frequency of 261 hertz, and the G above it. All you do is you take 3/2 and multiply it by the frequency of C, and you get 391.5 hertz. And so 391.5 divided by 261 is 3/2. You have this ratio between the different frequencies. And he also found similar relationships with the other intervals. The C here, 261, and here this is supposed to be an E note. Okay, the E, same thing. If you take the 5 quarters and multiply it by 261, you'll get 326. Okay, so that's if you divide 326 by 261, you get 5/4. Okay. So when you set the frequencies to these values, they sound really in tune with each other. Okay, 5/4, 3/2. This kind of has a list of the different ratios of frequencies to the starting, to C. So obviously, C's frequency divided by C's frequency is 1. Here, well, I'll just go through them. If you take the frequency of D and divide it by C, that's pretty much 9/8. Here's the 5/4 that I just mentioned. F is F4/3. G is 3/2. A is 5/3. B is 15/8, and the C above it is 2, because it's double the frequency of this. So, okay, let's see where I left off here. Now, this system sounds great when you play in one key, but if you switch keys, the new key's intervals have major tuning problems. So I'll demonstrate this example. In the key of C, G is equal to 3/2 C, right? 3/2 C. So in the key of C, the G note is 3/2 times C, the frequency of C. Also in the key of C, A is equal to 5/3 C. There's 5/3, and I just kind of like wrote the decimal for 5/3, which is 1.667 times C. Now, if you're going to switch keys, in the key of G, the A is also equal to 9/8 G. Okay, why is that? Look, well, look. A is the second of G. Okay, A is the second degree of the scale in G, right? D is the second degree of the scale in C. So any second degree of the scale, the frequency ratio is 9/8. Okay, so in the key of G, A is also equal to 9/8 times G. So if you take 9/8 and you also put in the value for G, which here we defined as 3/2, you'll multiply 9/8 by 3/2 times C, and that's 27/16 C. And in decimal, it's 1.687 times C, which is different than this, what you said about A over here. A in the key of C is 1.667, not 1.687. So you start running into big problems when you switch keys. So to solve these problems, the concept of equal temperament was developed. Now first I'll define it. Equal temperament is a system of tuning consisting of 12 halftone intervals in every octave where adjacent notes a halftone apart bear the constant ratio of the 12th root of 2, which equals to 1.05946. What does the 12th root of 2 mean? It just simply means that if you take the value x and you multiply it to the 12th power, you will get 2. Okay? So in this case, x is 1.05946. When you multiply 1.05946 12 times in a row, you get the number 2. Okay? So it has a great advantage that music can be played equally well in all keys. So let me discuss this a little bit. I think I did prepared a little thing on it here. Okay. So here are the 12 different degrees in the C in a range. C, C sharp, D, D sharp, and so on. Okay? So what is going on when you tune something to equal temperament? Well, if you start at 261 hertz, okay, what's happening is you just take the 12th root of 2, which is 1.059, and I just kind of like stop there, and you multiply it by 261, you're going to get 276.5, and that would be the frequency of C sharp, which is a semitone away from C. Okay? And if you take the new 276.5 and you multiply it by the same 12th root of 2, 1.059, you're going to get 292.94. And if you continue to do this all throughout, you are going to get the frequencies corresponding to equal temperament. Notice in each case there's going to be the frequency ratio between the adjacent notes is always the 1.059. 1.059, 1.059. So you multiply 1.059 12 times, you're going to get the frequency ratio is going to be, well, in this case it's 2.0, okay? Because the C above C is exactly 2 times the frequency, so 522 is twice 261, okay? So this allows you to play equally well in all keys, but it has the disadvantage that of the intervals that lie within a single octave, not a single one is in perfect tune. All the intervals, like the 3rd, the 5th, the 7th, they seem a little out of tune. This is why my guitar sounds a little out of tune after being perfectly intonated. It's a compromise. In order to play in all keys, you have to deal with this issue of all the intervals are not exactly what the ear wants to hear. So the piano and the guitar use equal temperament, obviously, because you can make chords with these instruments and they need to sound well in all keys. The frets on the guitar are spaced according to equal temperament. So I made something here to show that. Okay, so L is equal to the length of the string. So this is used to tell you where to place the frets when you're building a guitar. Where do you put those frets? So if you take L and you divide it by the 12th root of 2, 1.05946, this will be equal to the distance from the bridge to the first fret. If you take L and you divide it by 1.05946 squared, okay, this is the distance from the bridge to the second fret. L divided by 1.05946 cubed is equal to the distance from the bridge to the third fret, and so on. So this is how you would get those distances for a fret placement. And as an example, this would be a string length of 22 inches. From the bridge to the nut, okay, would be 22 inches. So if you take 22 inches, L is equal to 22, and you divide it by 1.05946, that will be 20.765 inches from the bridge to that first fret, and that's where you would put the fret. So this is pretty much how frets are laid out, and it's laid out according to equal temperament. So after my guitar is intonated and tuned, the B string always sounds sharp to me, especially if I play two string chord fragments using the B and G strings. If I lower the pitch of the B string slightly, many of the rock bar chords sound more in tune. But of course, if I play non-barred chords using the B string, they sound out. They will be out. So I once heard that Tom Schultz from the band Boston made a guitar set up for rock tunes in the key of E, and he made a separate guitar set up for the key of A. It sounds pretty extreme, but since rock uses overdriven, dirty sounds, guitar players prefer the just tuning in many instances. And you know, it's good to know that when violinists play and singers play, they usually use just intonation. So when they switch keys, they're switching all of their frequencies. So this is what the ear wants to hear. So this is going on during orchestra. Let's say there's a lot of instruments set up for equal temperament, but at the same time, a violinist or a singer is going to be seeking just intonation. So there's a lot of things that are slightly out, but in most cases it's not so bad because it provides like a chorus effect. So it kind of provides a rich sound, I guess. So that's pretty much the story of equal temperament. The last thing I wanted to talk a little bit about was sound intensity. So what is sound intensity? Okay, one of the measurements we use is Bell. It's equal to the change in intensity of a sound which results from a tenfold increase in the energy causing the sound. And a decibel is 1/10 of a bell. So what is this business? So the sound is measured using a log curve similar to the Richter scale. A lot of guitarists think that a 100-watt amp is twice as loud as a 50-watt amp, but in reality it produces only 3 dB more sound. So you calculate that by using this equation here, 10 times the log of whatever the power is, the wattage, let's say 100 watts divided by 50 watts, that would be 2. What's 10 times the log of 2? In this case it's going to be just 3, I think, 3 dB. It's not tenfold, you know. Twice as loud is tenfold, okay? So if you wanted to get an amp that was twice as loud as a 50-watt amp, you'd have to get a 500-watt amp, because 500 divided by 50 is 10, and the log of 10 is 1, and 1 times 10 is 10. That would be 10 dB. which is 10 dB is a bell, twice as loud. So I just wanted to mention that because there seems to be a lot of confusion about the wattage of amps and what it really means. Okay, I hope you enjoyed the video, and hope to see you in the next one.